So last time we talked about this idea of changing the order of integration. And so we're going to do one more example because there were so many great examples that involve changing order of integration that we just couldn't fit them all in. And we're going to get to do it again in our next session. In fact, there's a good chance that I might start the next time a few minutes early just because there's so much good stuff to say. But why do we change? Well, we change because we want things to be easier. And we don't change just for the sake of changing. We change because there are situations where changing our integral can simplify what we have to do. So we're going to do one more example, as I said. So here's this question. Evaluate the integral from -1 to 0, integral from 0 to 1, cosine of y cubed plus y, plus the integral from 0 to 3, integral square root of x over 3 to 1, cosine of y cubed plus y, and these are both integrals dy dx. Now, our first reaction is to say, how do we do this? Now, there's a temptation to say, this isn't so bad. We just take the antiderivative of cosine of y cubed plus y, which we might be tempted to say, maybe, well, that would be sine of y cubed plus y over 3y squared plus 1, right? Yeah, that's the temptation. We're not going to yield to that temptation because it's very wrong. So don't do that. Don't do that. So it turns out that there are a lot of things which are very, very hard to integrate. And you should not try to come up with new exotic rules. Use the old rules. They're the best. And so when you see something like cosine of y cubed plus y, and you're asked to integrate with respect to y, you're like, I don't think so. Is there another option? Well, what if we could integrate with respect to x? You're like, fantastic. I like that. Because then cosine of y cubed plus y would be a constant with respect to x, which means we have to change the order of integration. Now notice, I really have two integrals being added together. Now in some sense, it's very easy to change the order of integration here because this is a rectangle. So changing bounds in rectangles is very easy. But because it's the same function, probably it's a good idea not to think of these as two separate integrals, but rather as an integral that's been split into two parts. So we're going to think of these as two parts of a whole. So let's try to understand what's the whole. All right. So we're going to do a quick sketch here. So for this integral, what can we say? What's true about the x? -1 to 0, because the x is the outside, so the outside integral goes with the outside bounds. So I can say that on this integral, x goes from -1 to 0. What about y? What's true about y? 0 to 1. So, because remember, these are y equals 0, y equals 1. So this, like I said, it's a rectangle. X goes from -1 to 0, and y goes from 0 to 1. So, all right. So we'll come over here, and we'll make ourselves a little rectangle. There we go. So that's the first integral. All right, now the second integral, let's do that. Well, what can we say about x? X goes from 0 to 3. So 0 less than or equal to x less than or equal to 3. Where does y go from? Well, it goes from this function, square root of x over 3, less than or equal to y, less than or equal to 1. So where does that go? Well, 3, let's say 3 is out here, and at x equals 0, I'm 0. At x equals 3, it'll become the square root of 1. Well, that's at 1. Well, that's very convenient, because we're going to 1. So it's doing something like that. So this is the curve y equals the square root of x over 3. And that's the second integral. Okay, so if we think about what was happening here, in both of these integrals, our order was dy dx. Now dy dx says you're really slicing vertically. So we had to change it to two integrals because there was a change at 0. So let's now switch, because we're talking about we want to integrate with respect to x first. In other words, we want to get to something dx dy. Well, when we integrated dy dx, we needed two integrals. If we integrate dx dy, that means we're making our horizontal slices. How many integrals will we need? We'll just need one. One integral. One integral to rule them all. One integral to find them. One integral to bring them all. And then we'll get the answer. All right. Now, what happens? Well, we're going to have a single integral. The function doesn't change because we're not changing the function. We're just changing the way we're breaking things up. We're still integrating the same function. It's dx dy now instead of dy dx. And now we have to think, okay, well, let's talk about the outside. Y. Where does y go from? Where do I start my slicing? Where do I stop my slicing? Start at 0, end at 1. Those are nice numbers, 0 to 1. Now, next thing is we have to say, what about the next bounds? Well, these are my x bounds. So I look at my curve. So I'm on the left, I'm going from this curve. Well, what is that curve? X equals -1. And then, so that goes here, that's the left, or the lower. The upper is this curve, currently written as y equals the square root of x over 3. I say currently because we're going to change it, because we want to write it as x equals something, because these are my bounds for x. So x equals something. So y equals square root of x over 3. That says y squared is x over 3, which says that x is 3y squared. All right, 3y squared. Okay, so that's our first step. Well, we haven't done any evaluation. All we've done is rewriting. But rewriting is an important step oftentimes in working with integration problems. And you'll see this is a common theme over the course of the next few lectures. All right, now can we integrate cosine of y cubed plus y with respect to x? The answer is yes. And what do you get? X times cosine of y cubed plus y. So essentially this cosine of y cubed plus y, when I'm integrating with respect to x, acts like a constant. A very exotic looking constant, but a constant nonetheless. So it's a constant times x. Then I'm going to evaluate this from x equals -1 to x equals 3y squared. All right, so if we do that, I can say, well, what does this become? Integral from 0 to 1, the cosine of y cubed plus y, and then I'm going to plug in the x equals 3y squared, and then I'm going to subtract -1. So subtract -1 becomes the same as add 1. So that's what will happen once we do our evaluation. Now at this point, we're like, great, we're back to our problem. How do you integrate cosine of y cubed plus y? But it's not quite the same problem as before, because something has joined us in the mix. We have this extra term. Well, does that help us? It helps us a lot, because that's not just any random term. It's almost as if it was rigged so that it was the derivative of the inside. So y cubed plus y, derivative of that is 3y squared plus 1. And so this is probably a problem which we can do in our head now. What's the antiderivative of cosine of y cubed plus y times 3y squared plus 1? Sine of y cubed plus y. Evaluate from 0 to 1, becomes sine of 1 plus 1, also known as sine of 2. Subtract sine of 0 plus 0. Well, sine of 0 plus 0 is sine of 0, which is 0. So that's the final answer, sine of 2. All right. Now you might say, well, wait a second. What is sine of 2? And we happen to know the answer for that. Sine of 2 is sine of 2. And that's what it is. It is what it is. All right. Now on to today's topic. So for today's topic, we're going to continue talking about integrals. And we're still going to have similar regions. But now what we're going to do is talk about integration with respect to polar coordinates. Now, hopefully you all remember polar coordinates. It hasn't been quite that long since we've talked about them. So polar coordinates, it's a way to describe where you are. So just as a quick 1-minute refresher, Cartesian coordinates talk about where you are with two distances. You move this much in the x direction, you move this much in the y direction, and I'm at my location. The idea of polar is you say, let's fix everything in relationship to the center. You can call it your pole if you like. And if this is a point I want to get to, well, what I do is I say first, rotate an angle, theta, then go out a distance r. So r is a distance, it's a measurement of distance, a measurement of length. Theta is an angle. And remember that angles don't have length. We'll point out why that's important in just a few moments. So how do we go about integrating polar coordinates? Well, it's important to understand integration. And in particular, when you think about integrals, every integral that we're going to deal with always has three very important parts. And if we understand all three of these parts, we can do a lot. So what are the three parts of an integral? Well, there's the integral over the region. So you have to understand the region. And in particular, you have to be able to describe the region with whichever coordinate system you're using. There's the function. And you have to be able to say, what's the right way to write this function in my current coordinate system? Because you can rewrite functions by changing variables. This is something similar to what we talked about in our last part of the course, where we have the chain or where we had functions. In the functions, we can rewrite things by appropriate change of variables. And the last part, which oftentimes we forget about, but it's important to remember, is this dA. And that says, how do you break things into small parts? So if we understand all three of those things, how do we describe our region? What is our function in terms of our coordinates that we're using? And how do you break R into small parts? Then we can handle any integral. And in particular, we can switch from one set of coordinate systems to another set of coordinate systems. So I want to talk a little bit about this last part. How do you break things into small parts? And for this, it's good to understand what happens. So let's look at our two coordinate systems. So for Cartesian coordinate systems, what will happen is when we think about breaking things into small parts, our idea is to perturb our variables. Now in Cartesians, our variables are x and y. So when I perturb x a little bit and I perturb y a little bit, what I have is a little change in x, a little change in y, and so the result is a little tiny rectangle. So that's how you break things up in Cartesian coordinates, as little teeny tiny rectangles. Now when we talk about polar coordinates, what happens? Well, in polar coordinates, we're going to perturb our variables again. But our variables are now r and theta. So what happens is I do a little bit of change in r, and I do a little bit of change in theta, and what I get is I get this piece here. It's not actually quite a rectangle because it's a bit curved. It's like we're looking at the crust on a pizza or a pie or something. But, you know, this is a little bit of a bend to it. So this is the basic shapes that we're breaking up our polar coordinates into. Now, we have to understand the basic shapes, but one of the things we have to understand is what's the area. Now, Cartesian, very easy. because we know rectangles. Dx, dy, dy, dx. And it also makes sense because when we're talking about area, you should have two lengths involved. All right, so if you think about y is a length and x is a length, that's two lengths, so that should give us an area. So that makes sense, that to have dy dx or dx dy produce an area. Now in polar, what will happen is we have to say, well, what's the right area? Well, the temptation is to say dr d theta. That won't work. Why won't dr d theta work? Well, you think about it, r is a length, which is good, but theta is not. It's an angle, and angles actually don't have units attached to them. So if I just had dr d theta, that would not be the right kind of thing. It would only have one length. So there has to be a little bit more. It turns out that the correct term is r dr d theta. Now, how do you see that? Well, there's a couple of ways to see it. One way to see it is to say, let me think about this. It's not quite a rectangle, but it's rectangle-esque. And I really only care about small changes in r, small changes in theta. And in that case, it really is very close to a rectangle. In fact, you might look at this and say, are you sure that's not a rectangle? Because it's hard to see the bend. But it's not. Do we know what this length is here?
R d theta.
Well, it turns out it's r d theta, yes. Now, how do you get that? Well, one way to get that is to just think about it in terms of saying, suppose I have an angle theta here. What's all the way around? That's also known as the circumference. And if I have a radius r, all the way around would be 2 pi r. Now, if I have an angle, what's the full revolution? 2 pi. So, now you say, look, all the way around is 2 pi r in terms of circumference, all the way around is 2 pi in terms of an angle. So we look at the ratio, the amount of turn that we've gone, the proportion of a revolution that we have is the same as the amount of surface area we'll get on the edge. And now if you clean that up, it becomes L equals r times theta. Well, in our case, it's d theta. It's a small change in theta. So if you see that, we say, okay, well, look, that's roughly r d theta, and then times dr gives us r dr d theta. Now, you can do it in either order, r dr d theta or r d theta dr. I will tell you that 99% of the time, you will probably be using this variation, the r dr d theta. And that's because when we were growing up last semester doing things in polar coordinates, we tended to say, let's describe things in terms of theta. So r is a function of theta. So because we tend to describe things in terms of theta, the dr d theta is the best way to go. All right, well, let us try some examples out. So, here we go. Find the integral 0 to pi, integral 0 to theta, pi minus r times r dr d theta. Okay, well, what do we do? Well, here, the answer is we just integrate. Well, almost just integrate. Notice that this is integral 0 to pi. I can multiply the r through. Integral 0 to theta, pi r minus r squared dr d theta. And that becomes integral 0 to pi. What is the integral of pi r minus r squared? With respect to r. We should always remember what we're integrating with respect to. 1/2 pi r squared minus 1/3 r cubed. Okay. And then we're going to evaluate. This was an r integral from r equals 0 to r equals theta, d theta. So this becomes integral 0 to pi 1/2 pi theta squared minus 1/3 theta cubed. Okay, d theta. Next, well, we integrate again. These integrals are so nice, we're going to keep doing them. All right, what's the integral of 1/2 pi theta squared with respect to theta? 1/6 pi theta cubed minus 1/12 theta to the fourth. Now you should say, this feels really familiar. Like it's kind of the same thing as we did before, but with different symbols. Because it's kind of like the same thing you did before, but with different symbols. So it should feel familiar. In other words, the processes haven't really changed. We're almost there. Plug in pi. You get 1/6 pi times pi cubed, which is pi to the fourth, minus 1/12 pi to the fourth. And then we're going to end up subtracting 0, because 0 is our favorite number to work with, which ends up being 1/12 pi to the fourth. Now, the question is, what did we just find? Well, there's two possibilities that it could be. So let's think about what they are. Well, one possibility is to say the following, to say, you know, if I think of it not in terms of polar, I can think of it in the following way, is I have here in r theta plane, doesn't really matter, and what happens? Well, theta goes 0 to pi, so here's theta going from 0 to pi, and r goes from 0 to theta, which means it would be a triangle here. So r going from 0 out to the value theta. So I could say, look, what I did is I integrate over this rectangle where my function was the following function, pi minus r times r. In other words, maybe this wasn't even polar coordinates. It was just like, I just threw in extra symbols, r and theta. But maybe it was polar coordinates. If it was polar coordinates, well, what does that say? Well, let's see what it says. What can you tell me about my bounds here? What's true about theta? Yeah, theta goes from 0 to pi, which is what it says up here. What's true about r? Well, r goes from 0 to where? Theta. All right. Well, the curve r equals theta is actually a famous curve. This curve, Archimedes' spiral. So this is r equals theta in the polar coordinates. And now, that's what we're doing. We're going from theta equals 0 to theta equals pi. But what's the function? Which function would we be integrating here? Yeah, in this case, the function would be pi minus r. In other words, we wouldn't have the r anymore. It would be pi minus r. Now, why is it pi minus r, not r dr d theta? Sorry, pi minus r times r. Whoops, gave it away. Okay. The key here is in polar coordinates, I have to have this r attached to dr d theta. Whereas if I think of this as being somehow a rectangular coordinate system, just with weird symbol names, the r becomes attached to the function. So, what's the correct interpretation? And the answer is, both are valid. What's the way we'll usually think of it? Well, we'll usually think of it in terms of the polar coordinates. But it often comes down to how do you choose to interpret the integral? What does it become? It's whatever you need to do to interpret it. That's the answer. All right. Let's try something else. Let R be the region in the first quadrant where 1 is less than or equal to x squared plus y squared, and that's less than or equal to 9. And let's find the integral over R of log of x squared plus y squared dA. Oh, well, this is nice. No polar coordinates here. Okay. Now notice it doesn't say anything about polar coordinates in this problem. Is this an appropriate question for today's lecture? Yeah. We should be suspicious, first off, that we're talking about it today is a big clue. Okay, but, you know, there's some other things that give it away. Let's talk about our region. We're in the first quadrant, and we're told x squared plus y squared is between 1 and 9. Well, x squared plus y squared equals 1 is a circle. What circle is it? Circle with radius 1. X squared plus y squared equals 9 is also a circle. Which circle? Radius 3. So, pretend these are actually drawn correctly. All right. So our region here is this region. And you'll notice that this region is not the greatest region to talk about if we're using rectangular coordinate systems. Because rectangular coordinate systems, they like boxes. And they do okay with straight lines. But once you start throwing in circles, they're like, all right, be ready for square roots. And you've hopefully learned our lesson. Square roots are tough. All right. So in Cartesian coordinates, this is not a pleasant system to work with, so not a pleasant region to work with. However, in polar coordinates, what would this become? So let's talk about polar. Polar would say we need theta and r. What's true in polar?
0 to half pi.
Okay, so theta goes from 0 to 1/2 of pi. What about for r?
3 to 1 to 3.
R goes from 1 to 3. So think about polar. You always think about how it relates from the center. So I'm going out, and what's happening is if I head out, I'm going to start at 1, I'm going to go until I hit 3. So I'm going from 1 to 3, and that's true from 0, and it keeps being true all the way until I get to pi over 2. So you'll notice that this part right here, there's a technical term in math called nice, because it's clean, very clean description. And we like things which are nice. All right. So there's something else that suggests polar. Notice this x squared plus y squared on the inside. Now, it's possible for us to figure out log of x squared plus y squared if we're integrating in Cartesian coordinates. We do integration by parts. We would silently curse the problem, but we could get through it. But in polar, what happens to x squared plus y squared? It becomes r squared. So let's think about how we write this integral. And remember, every integral has 3 pieces. The region R, the function, and how we break up. Now we said we're going into polar, so that says the way we break up is r dr d theta. All right. How about the function? Well, log of x squared plus y squared will become log of r squared. And our bounds. Well, our theta bounds are 0 to pi over 2. And our r bounds are 1 to 3. And now we have our integral. And this is not so bad. We can do one little quick thing. The 2 actually can come down because of the log. So this is the integral 0 to pi over 2, integral 1 to 3, 2 log r dr d theta. And this is actually a case where we can pull things into 2 integrals. Because if you look at our integral right now, there's this inner part here. Ignore the theta for a second. What's true about our inner part? It's going to be a number. There's no theta at all. So what I can do is I can say, well, this is a constant. So I can really say, I can break this integral up into 2 parts. There's the integral 0 to pi halves d theta, And then there's the integral 1 to 3 to log r dr. So this is one of our we can pull integrals apart kind of ideas. Now one of these two integrals is easier than the other. So maybe we'll take turns. Which one do you want to do? And I'll do the other one. Do you want to integrate with respect to theta or with respect to r? You want to do the theta one? Okay, you can do the theta one. What is the integral? 0 to pi halves of d theta. Pi halves. Okay, good. All right. Your job is done. Now, my job. All right. Integral of 2 log of r times r dr. Well, for these, you can do integration by parts. I mean, you'd obviously say, look, the log r, that would be the part we want to differentiate. The 2r part we integrate. So you'd have uv would become r squared log of r. And then we have to say, okay, that's what we want. And then we have to subtract off the right thing. And the right thing is 1/2 r squared. So that's what it'll turn out to be. Now, if you're skeptical, and it's fair for you to be skeptical, just take the derivative. Product rule. 2r times log r, well, that's good. Then r squared times 1/r, leaving with r. But here, if I take the derivative, I get minus r, which means the r's cancel what I claim. Evaluated from 1 to 3, so we still have the pi halves. Then we have 9 log of 3 minus 9 halves. Subtract 1 log of 1 minus 1/2. Well, log of 1 is 0. That goes away. Minus minus makes a plus. So instead of minus 9 halves, it's really minus 8 halves, also known as minus 4, because that's minus 4.5. So end up with pi halves, 9 log of 3 minus 4. And there we go. Good, done. Well, so what did we learn? Well, what we've learned is it's possible that it's to our advantage to sometimes switch to polar coordinates. What do we look for? Well, we look for certain things. Does the function become simpler in our new coordinate system? In other words, if I switch to polar, do I get something that's easier? One thing to look for, x squared plus y squared. If you see x squared plus y squared, you're like, that looks like polar. The other thing is, look at your region. Does it simplify in polar? Or maybe your region is given in terms of polar. That's a big clue. If something is given in polar, you should probably do polar. But, all right. Let's try another one. Okay. I thought we were doing polar today. Find integral 0 to 1, integral 0 to square root of 1 minus y squared, sine of x squared plus y squared, dx dy. Well, what do we do? Any ideas? Yeah, let's draw a region. Now, one thing we should not do is try to integrate that. Because if you try to integrate sine of x squared plus y squared with respect to x, forget it. It's not going to work. You say, okay, let's do the trick we did at the start of class. Let's switch. Maybe if we integrate first with respect to y. No, still not going to work. Okay, so look, it's not enough to just change the order of integration. We have to fundamentally change the way we approach this problem. That's all right. We like fundamental changes. Draw a region. Well, what does the outer bounds go with? Well, that's y. So what's true about y? 0 to 1. Now, inner bounds. These are x bounds. So remember, this is not just 0. It's x equals 0. And it's not just square root of 1 minus y squared. It's x equals square root of 1 minus y squared. So 0 less than or equal to x less than or equal to square root of 1 minus y squared. All right. So our region. Well, what does x equal the square root of 1 minus y squared look like? It's what? It's a circle. It's a circle. Now you might say it doesn't look like a circle, But think about what would happen if you squared it. X squared is 1 minus y squared. And then you would move stuff around. X squared plus y squared equals 1. So that's part of the circle. Now, which part? Well, y goes between 0 and 1, and x is above 0, so we're looking for that part of the circle. 1/4 of the circle. All right. So, in light of what we've talked about, perhaps it's a good idea to switch to polar, especially because we can't do anything in Cartesian. So, that's another good reason to switch. If you can't do anything, try something else. So, let's think about what happens. Now, previously we had dA. Notice dx, dy. This is our dA in Cartesian coordinates. So, what's going to happen is that the dx, dy is going to transform into what? Yeah. So, this is going to become r dr d theta. So that will go somewhere. Let's say here. Hopefully I don't regret that choice. So that's how I'm breaking up. I'm accounting for that. Now let's talk about the function. Sine of x squared plus y squared. What will that become? Sine of what? Sine of r squared. Good. Now let's talk about our bounds. We're definitely not going to copy these bounds down because these are x and y bounds. Wrong kind of things. Theta bounds. What's true about theta? Where does theta go from? 0 to pi over 2. And let's talk about r. Now, we didn't write it down, but this was a unit circle. Where does r go from? 0 to 1. All right. Good. Well, can we integrate sine of r squared r dr? If it helps, we can put a 2 there and a 1/2 out in front. And you're probably thinking, why would that help? Well, maybe. If it doesn't help, you can still do it. Do we know the antiderivative of sine of r squared times 2r dr? Yeah, negative cosine of r squared. Evaluated from r equals 0 to r equals 1 d theta. Well, so we evaluate. So we have 1/2, still have this integral floating along. That'll become minus cosine of 1. Plug in 0. You get cosine of 0. Now cosine of 0, we do know, what is cosine of 0? It's 1. So minus 1 makes plus 1 d theta. And there's not much you can do to cosine 1. It is some number, but we don't really have a good value for it. And this is a constant. It's like, oh, we should have done the thing we did last time, which is break it apart. Yeah, we should have. But that's okay. We'll still get the right answer. Integral d theta is theta, evaluated from 0 to pi halves, which will give us pi halves. We have another half there in front, so you get pi fourths times 1 minus cosine of 1. And that's our answer. Good. Okay. Well, another example. Find C so that the volume for the set of points with x squared plus y squared is less than or equal to z, and less than or equal to c is 8. Well, so we're looking for a volume, and we want the volume to equal 8. Let's think about what we're talking about. So we're looking for a set of points, which means we have a shape. We have some shape, and we want the size of our shape to be 8. And what does our shape look like? Well, on the bottom part of the shape is this x squared plus y squared equals z. What does x squared plus y squared equals z look like? There's some wonderful miming going on, which is, it looks like a bowl. So it's almost like you took a parabola and rotated it, because you take a parabola and you rotate it. That's what you get. So it's a bowl shape. So that's z equals x squared plus y squared. Now, of course, I sort of stopped it because, my paper doesn't go forever. But I also stopped it because notice there's a top. Z equals c. What does z equals c look like? It's a plane. A plane. It's a flat plane at height c. So there's z equals c. Okay. Well, so let's see if we can find the volume of this bowl. Now notice what would happen. Well, if you drop this straight down, so you were saying, where is this sitting on top of? Well, one way to find where it's sitting on top of is saying, where do the two curves intersect? They intersect where x squared plus y squared is equal to c. Well, that means that the region here, our region R, is the circle of radius square root of c. So that's our region that we're integrating over in the xy plane. So the volume is the integral over our region. Now, how do you find volume? What do you integrate? So there's a couple ways to find volume. So sort of when we talked about starting integration in multivariable, which was a long time ago, like Monday, we said if you're thinking about volume, it's like you're adding up the sums where you have little bits of area on the bottom times the height. So what we're going to do is to find volume, what you integrate is you have your little bits of area, that's your dA, and then what goes into here is your height. That's the way you find volume. So what's the height? Well, the height is from the top curve, which is, sorry, not the top curve, top surface, C, to the bottom surface, x squared plus y squared. So that's the distance between these two surfaces. That's your height. So that's what we need to integrate. All right. So we also know our volume should be 8. So 8 should be our volume, which should be the integral over our region of c minus x squared plus y squared dA. All right, well, that's what we have. And we need to solve for c. Let's think about how we actually can work this integral. Now, because it's polar coordinate day, let's try polar coordinates. It's a good idea. How can we describe our region in terms of polar coordinates? So again, if we look at just in the plane, so here we are in the plane, what we see is our region is a circle of radius square root of c. So what can you say about theta? What can you say about r? Theta goes all the way around, so between 0 and 2 pi. What about r? Where do we go from? 0 to the square root of c. So we have that our volume is going to be equal to the integral. Our function, we're going to switch to polar, so it's becomes c minus r squared. Our dA is r dr d theta. Our bounds, theta, that's the outside, so that's 0 to 2 pi. Next, our inside is r, that's 0 to root c. Now you can split this integral into two pieces. You have your integral 0 to 2 pi d theta, and integral 0 to square root of c, c minus, well, I'll say cr minus r cubed dr. Because it turns out the bounds here, you'll notice there's no, these are all numbers. Now you might say, wait a second, we don't know c. C's not a number. Well, it will be. We just have to figure it out. It's not something that varies. The first integral, very straightforward, 2 pi. The second integral, not too bad. CR, antiderivative, is 1/2 CR squared. Remember, C is just a number. integral of r cubed, 1/4 r to the 4th. And we're going to evaluate from 0 to square root of c. Well, so what do we get? We get 2 pi, 1/2 times c, because square root of c squared will be c. So that's 1/2 c squared. Then minus 1/4 square root of c to the 4th becomes c squared. Well, that's very convenient. 1/2 minus a 4th is a 4th times 2. That'll become 1/2 pi c squared. Now, what do we need? We need 1/2 pi times c squared has to equal 8, because just follow the equal signs. So, rounding the corner, we see the end in sight. Move the 1/2 pi across, c squared has to equal 16 over pi. And so, take the square root, c is equal to 4 over square root of pi. And we're done. And we're done. And I think we really are done, because the next one is more interesting than 2 minutes. So we'll see you next time.